Hello students, welcome to this lecture on the interconnects, and especially in this particular lecture we will talk about the crosstalk effects between the interconnects on the same layer, right? So we have multiple layers in a silicon on-chip design, and if especially we have a lot of stacked metal layers. But in this particular lecture, we are going to talk about the interconnects in the same layer and its how it affects the other interconnects, even if it is not switching or if it is switching. All right. So let's begin with this particular lecture. So here, I've just drawn a block diagram representation showing two wires, the wires A here and then the wire B here. And individual wires will have its own capacitance with respect to the another layer of metal. I have just represented it in the form of a ground layer or a ground plane. So that's why these two are indicated as a ground symbol. And it will have its own resistance. The wire A will have its own resistance. The wire B will have its own resistance, and it will have its. It can be characterized with a capacitance as well. So a CA capacitance for the wire A and a CB capacitance for the wire B. Between them, I think between these wires, the wire A and B, there is a dielectric, and which gives an adjacent capacitance between the wire A and B, and that's why I have drawn or denoted an adjacent capacitance as well between the wires A and B. And I've said that okay, this particular wire is kind of connected to the ground, so that is perfectly fine. So what we are seeing here is if there is a small change, or rather, if in a digital circuit, if there is a change from 0 to VDD or to logic 1 here, so I will have a change in the wire A that will be kind of propagated from the one side of the wire to the other side. But because of this coupling capacitance or the adjacent capacitance, there will be an effect on the wire B as well. All right. So even if the wire B, if it is not holding the ground, if it is at logic 0, and let's say that it is not being driven by any of the circuits, it is having a floating voltage of 0, a change here in the wire A will have a coupling effect or a crosstalk on the wire B. So I will have some kind of a change in the voltage for the wire B, and that is called as a crosstalk effect. Right, so it is named as a crosstalk because it is actually the communication between the wire A here transferring the signal, the change in the logic here from one end to other end, which is unnecessary getting coupled into the wire B, and wire B doesn't have any intention of the change in the voltage here. It is getting the coupling effect from the wire A, right, and that's the reason why it is called as kind of a crosstalk. It is hearing whatever the wire A is communicating or talking, and that's why it is called as a crosstalk effect. Moving ahead, so let's say that this wire B is not connected anywhere. It is not driven by any other circuit. So I have this particular capacitive representation of this two wires A and B. Between them there is a adjacent capacitance. And wire A has a small change in the form of delta V input. So if I actually represent this in an L model for the wire A and B, and in between there's an adjacent capacitance, this is how the overall circuit looks like. So delta V in applied to the wire A, which can be represented in the L model as RA and then CA. And then we have this C adjacent, and then the wire B, which could be represented in the L model. So RB and CB. CB is connected to the ground. And this particular node is kind of left floating. So the question is, if this is the point B, and then let's say this is the point A. All right. So the change in the A, what will be the change in the B? Right. So if I can take out this resistance RA and RB, make it just for our own assumption, making it much simpler. If I make this resistance to be 0, so this is point A, which sees a capacitance of CA, and then in between point A and B we have a C adjacent or the coupling capacitance, and then B to ground we have a CP. So a change in A will have a change in B, and that change we can easily evaluate or estimate using the voltage divider method. So this is what we will have. Delta VB will be nothing but the voltage divider. This is the X represents the impedance of the capacitance. So we will eventually get delta VB, the change in the wire B due to the change in the wire A. The change in the wire A is intentional. The change in the wire B is unintentional, right? That is not expected and that is something unwanted. But still, because the change in the wire A is there, change in the voltage for the wire A is there, we will have some kind of a coupling effect on the wire B, and that particular change will be nothing but given in this particular expression, right, where it is delta VA multiplied by C adjacent by C adjacent plus CB. So impact on the B due to the change in A wire is given in this this particular expression. So if delta VB is delta VA is 1 volts and then C adjacent and CB, if it turns out to be the same, then if I can rewrite this as if it is 1 volt change, because in a digital logic, especially in a 65 nanometer technology node, the logic at this particular end will be changing from 0 to 1. So the change in delta VA, if it is 1 volts, then the change in delta VB, assuming C adjacent and CB are same, then we will get something like 0.5 volts. Right, so this will be the impact, right, on B due to the change in the wire A. Right, hope this is clear. Moving ahead, so if the wire B is carrying a load of C load, so that means that the wire B, which was initially floating, let's say it is driving another load, it is driving another circuit or an inverter or any other combinatorial circuit, then we can also represent that particular circuit on the load side with a C load capacitance, or a C input capacitance of that particular circuit will be loaded into this particular wire. Then the overall change in B will be nothing but delta VA by C adjacent divided by C adjacent plus CB plus C load, right? So having a load or having the wire B driven by, the wire B driving another circuit will be useful in reducing the overall crosstalk effect, because this particular parameter, it can increase the denominator and then overall my delta VB is likely to reduce. So now if I have a C load is equal to CB is equal to C adjacent, in that sense I will have delta VA, which is anyways 1 volts. We are considering 1 volts, then delta VB will be 1 volts, 1 divided by actually 3 if all the capacitances are same. So it turns out to be 0.33 volts, which is less than that of what we had seen earlier of 0.5 volts. So having a C load or having the wire B connected to some particular circuit, connected to some or driving to some particular combinatorial gate circuits, that will be very useful. Now let's take a look at this particular the circuit or the representations. And here I have the wire A and the wire B and its associated capacitances. I have neglected the resistance at this particular point of time, and we will once again use the resistance or include the resistance to estimate whether it is a performance or the power later on. Right, so we have a wire A and wire B, which are we can say that it is close by, and then we have this C adjacent capacitance, and the individual of this wire with respect to its layer below or above, whatever it is, it will have its capacitance CA and then CB for the wire A and B respectively. Right, so I have drawn a table here just to find out what is the effective capacitance that we have to consider for a change in the voltage, for the wire A and the change in the voltage for the wire B. Right, so what is that effective capacitance so that I have to consider? Right, especially for, let me pick this wire A. So let me pick this wire. So what is that effective capacitance? Whether it is CA plus C adjacent, that I have to consider, because, if there is a change in the voltage here from 0 to 1 volts for the wire A, and let's say that the B is grounded, right? It's a grounded or connected to the VDD rail through a transistor. Let's say, there is some particular inverter or a circuit which is driving this wire, right? It's not loading, it is driving this wire. So based on that particular logic, input logic, it will either be connected to ground or it will be connected to the VDD. So let's say that this is at a constant voltage or a constant logic. And then if I have a change here in the wire A from 0 to 1 or 1 to 0, right? What is the effective capacitance I need to consider for the wire A so that it actually charges or it discharges. Right? So if I have an effective capacitance, then I can estimate the overall delay for this particular conditions, right? When the wire A is doing the transition and wire B is held constant. Okay, so that will be one case. So let's look at this first case. A is switching, the wire A is switching from 0 to 1 volts. B is held constant either to 0 volts or to VDD rail or to the logic high. So the delta V, the change in the voltage for the wire A will be nothing but VDD. So 0 to VDD or 0 to 1 volts. So the charge that this particular driver circuit has to charge, that will be, it has to charge this capacitance CA, it has to charge this capacitance C adjacent. CB is anyways held constant, so no need to charge the CB capacitance. So the overall charge will be nothing but CA plus CD, C adjacent, CA plus C adjacent multiplied by the VDD. That's the change in the voltage. Right. So what I'm saying is, if I have a change, step input here from 0 to 1 volts, then I will have to charge the CA capacitance. I have to charge the C adjacent capacitance. So the overall charge will be CA plus C adjacent. Right, so that is, this particular 0 to 1 volts change will be brought by a driver circuit here, which will be driving this particular wire. Right, so a driver circuit is connected, the output of the driver circuit is connected by an interconnect to another circuit. So if you assume that, then a change here 0 to 1 volts will have to charge the capacitance CA and the C adjacent. And similarly, if it is doing the other way from 1 to 0, then the CA and C adjacent has to discharge. So the overall charge in this particular case will be nothing but CA plus C adjacent multiplied by VDD. Right? It could be either the charging or the discharging. So the C effective capacitance that we have to consider for this particular case of the wire A when it is switching will be nothing but C adjacent plus CA. Right? Hope this is clear. The second case, wire A and wire B. So wire A is actually switching, right, from either from 0 to 1 or 1 to 0. Wire B now, it is not held constant. So wire B is not held constant. So let me pick up a small eraser. So I'm going to say that this is not held constant. In fact, it is actually it is also changing in the same directions. So it is also changing in the same direction in the sense if the wire A is changing from 0 to 1. So this, if I pick, wire B is also changing from 0 to 1. So if wire B is also changing from 0 to 1, so initially the voltage in the C adjacent when it was 0 and then 0, it was the 0 voltage across the C adjacent. And then when it has moved to 1 volts on the wire A and then moved to the 1 volts on the wire B, the C adjacent, the potential difference between the C adjacent capacitance will still be 0. So actually there is no charge that is being delivered to the C adjacent, or rather the charge stored in the C adjacent is actually 0. So the delta V in this case, that has to be provided by the driver circuit A here. Driver circuit which is driving the interconnect A will be 0. So the total charge Q will be nothing but C adjacent multiplied by 0 plus, so it has to charge only the C capacitance. Right, so CA into VDD. So the effective capacitance will only be CA. So C adjacent doesn't come into the picture because the wire A and wire B are actually doing the same side, in the same way it is actually doing the transition from 0 to 1 volts or 1 volts to 0 volts. So in both the cases, the potential difference across the C adjacent will be 0. That means there is no supply or the discharging of the charges that has been stored in the C adjacent. The third case, A is switching. Let's say it is switching from 0 to 1 volts. But now B is actually switching in an opposite direction. So if A switches from 0 to 1 volts, A switches from 0 to 1 volts, then the B actually switches from 1 to 0 volts. Right? So if B switches from 1 to 0 volts. So the overall charge that has been, that needs to be delivered to the C adjacent, right? That needs to be delivered to the C adjacent by this particular driver circuit will be nothing but 2 VDD, because the potential difference here is, it has been changed to 2 VDD times. So initially the C adjacent was, if I pick the C adjacent, initially it was 1 volts here, it was 0 volts here. So the potential difference was minus 1 volts. And now it has become 1 volts here and 0 volts here. So it is basically 2 VDD or 2 volts, the change in the potential difference. That means the total charge that it needs to be accumulated to the C adjacent will be twice, right? So it will be twice VDD multiplied by C adjacent plus CA into VDD, right? So anyways, this has to be charged because it is rising from 0 to 1 volts. So the C has to be charged from for VDD. So the effective capacitance in this case with respect to the VDD, with respect to the the driver circuit connected to the interconnect A will be VDD. So in that sense, the overall capacitance will be 2C adjacent plus CA. So notice that we have got 3 cases. In one case, it is the minimum C adjacent, and in another case, it is the maximum. So the maximum C effective capacitance will be useful in estimating the propagation delay, whether it is falling or rising, and the minimum one should be useful in calculating the contamination delay, falling or rising, right? Because the less capacitance is likely to have a less delay, right? So going forward, let's say that I have a wire A and B and its adjacent capacitance is 0.12 femtofarads per micron. So that has been characterized. So based on the length of the wire, length of the A and the B wire, we can estimate that what should be the C adjacent capacitance. In fact, it turns out that whatever is the, whichever length is minimum here, if A is 1 mm and B is 2 mm, then the adjacent capacitance will always be with respect to the 1 mm. So whatever is kind of, aligned. So in that sense, what I'm saying is, if suppose A is this wire, this is of 1 mm, and let's say B is of 2 mm. So this is the wire B. So the capacitance will be nothing but with respect to this overlapping region, and then this particular capacitance C adjacent will be nothing but 0.12 femtofarads per micron multiplied by the 1 mm which is overlapping, right? It's basically based on the A and B wire, which how much ever is the length that has been overlapping between the two wires, that will be used for calculating the C adjacent capacitance. And of course, we have the CA and CB, which is 0.08 femtofarads per micron, and then 0.08 femtofarads per micron for the CA and CB capacitance. There are 2 driver circuits. So inverter is there. Inverter is driving this interconnect. So its switching resistance is given as 1 kilo ohms, and its switching resistance is given as 1 kilo ohms. The length of the wire is 1 mm. So if it is 1 mm wire, and let's say that wire A and B are aligned properly, then that means that the overlapping length is still 1 mm. So then in that case, I should be able to find out what is C adjacent and CA and CB. CA is nothing but 0.08 femtofarads per micron multiplied by 1000 micron will give me 0.08 picofarads. CB is also same, 0.08 picofarads. C adjacent will be 0.12 picofarads. What we need to find is the delay of the circuit. So we need to find out the TCD and TPD. Right, propagation delay and contamination delay. For propagation delay, the effective capacitance is nothing but 2C adjacent plus CA, and for the contamination delay, we know that this is nothing but CA. Right, so if I consider one of the driving circuit driving this particular interconnect, so how much time it will take from one end of the wire to reach to the other end of the wire with this adjacent capacitance and with this CA capacitance, its own wire capacitance. Right, so in that sense, TPD is when A and B are switching in the opposite direction, and so in that case, TPD will be nothing but R switching of A, which is labeled as R effective here, and then multiplied by CA plus 2C adjacent. So it is 0.08 picofarads plus 2 times 0.12 picofarads will be 0.24, so it will be 0.32 nanoseconds or 320 picoseconds. So that will be the propagation delay. And for the contamination delay, it is R effective into CA. C adjacent is anyway 0. So it will be 1 kilo ohms multiplied by 0.08 picofarads, which will be 80 picoseconds. right? TCD is when A and B are switching in the same direction.